So you get 3 measurements in one, although not with closure, because all of your errors in the first 2 measurements go into your error in the calculation of B. We calibrate them with pure water. And so you're measuring the absorption of seawater or suspensions relative to pure water. So your absorption will contain all of the optical properties of anything dissolved, be it organic or inorganic. I already showed you how pure water's absorption properties change as a function of temperature, so you have to correct for temperature differences between your calibration water and your sample. Going back to what our theory told us about measuring attenuation and absorption in our little infinitesimal volume, these are not ideal, and we have to make corrections for the fact that they collect scattered light or don't collect scattered light so that we can get to the actual measurements that we want. Okay, so we're going to give you some strategies for robust measurements. All right. The measurement reality for all sensors. So this is a reflecting tube absorption meter. The cuvette is a round cuvette. It's made of quartz, so that when light comes in and it may scatter, there's the difference in index of refraction between the water, the quartz, and the air is such that you get a lot of internal reflection, so that most of the scattered light ends up out the end where it interacts with a diffuser and then a detector. So it collects most of the forward scattered light, about the first 40 degrees of the volume scattering function. The beam C size wants to minimize the scattered light. Why would they want to do that? Why don't you want to collect scattered light on the C side? Because you will underestimate the attenuation, because attenuation is absorption plus scattering. So what you'd like to do is have an infinitesimally small detector here so that even 0.1 degree scattered light gets excluded. So Emmanuel will talk about this a little bit more, but you don't want to collect scattered light to measure beam C. You do want to collect scattered light to measure A.
But wouldn't this make your absorption larger to collect the scattered light with because the path will be longer?
Exactly. But it will be smaller than if you didn't collect the scattered light. If this scattered beam went out and didn't go to the detector, you would call it absorption. So you're collecting all of this scattered light, which is increasing the optical path length, but then at least you're collecting that photon on the other end. But that's exactly one of the corrections that you have to think about. And you're not going to collect that one at all. Right, that one's going to either go out or scatter back or something. You'll never see that one, and you will call that absorption, even though it was scattering. Okay, so you derive the scattering by the difference between attenuation and absorption. Okay, so some of the scattered light's not collected by the absorption tube, and that leads to the overestimation of absorption, and so you have to correct for that. Okay, some of the scattered light is collected by the attenuation tube, and that leads to an underestimation of beam attenuation. And so the way that we deal with it currently is to report the detection angle so that you know how much you are likely collecting. Is there any correction factor? I don't know of one. Unless you know your volume scattering function. If you know your volume scattering function, why do you have an AC9?
Exactly.
Okay.
So, I have a paper. With us. Yeah.
But you have to know the volume scattering function or estimate it. Yeah. Yeah.
And it's vulnerable.
And what?
We talk about it. We have a whole lecture on beam attenuation.
Yeah.
We'll get to this. But
Upload your paper. I can't remember what the correction was. How much it was. Was it significant? Your volume scattering function. Yeah. Yeah.
So the issue is, in some respect, what Collin said, beam attenuation is a theoretical construct. In the case in which the theoretical beam attenuation, in which you collect I mean, you collect only scattered parts, so you can never got scattered.
Yeah.
Really, the realism of the measurement is you're going to collect some. The question is, you can decide to correct, or you decide to report your accepted sample.
Exactly.
Just make sure that whenever you compare it to another one, it's one that has a similar result.
And just like the previous situation where we were talking about discrete samples in the lab, obviously if you have a really optically thick sample with lots of particles in it, you're going to get lots of scattering events in here that are going to change, are going to increase the amount that you miss, they're going to increase the path length. And so also understanding what the limitations of linearity are really important in these sensors. Don't use a 25 centimeter AC meter in the Amazon. Right? I don't even know if you can use a 5 centimeter one, right? I don't think you can because there's so much, it'll increase so much the path length amplification. So know your instrument, know your environment, know what your limits are. If you're outside the limits of linearity, don't even bother collecting the data because you can't, it's not good quality because it's not obeying what we know, what we are desiring in the theoretical estimation of absorption. Okay, so you buy your AC instrument. A year later, you get it from the factory. No, I'm just kidding. Not really. You get it from the factory. It comes with a calibration coefficient. They have measured the calibration coefficient relative to pure water as a function of temperature, and you know your response of the instrument to that temperature. The first thing you do is you calibrate it in the lab for yourself to make sure that nothing happened during shipping. So you calibrate it with pure water and you know the temperature. Then you're ready to deploy it. You put it on your frame, or you put it in your flow through, or you put it on your mooring, or whatever the structure is that you're going to deploy it. And you make sure that all of the tubing is covered. See, this one wasn't covered. Tubing is covered with black tape all the way up because light will just funnel down this like an optical fiber into your sensor. So make sure that it's all taped up. You'll notice in the lab today, everything is taped up. If you want to deploy it outside, it's good to put some copper tubing in there that tends to reduce biofouling. This air valve helps keep the bubbles out so that when you pump your water through, the bubbles get released. The type of frame that you put it in, basically seat the bottom, which means put it in a cup. And then you clamp the top. You don't clamp the top and the bottom, or you can change the alignment and actually the beam won't be traveling straight anymore because the light beam is traveling through your cuvettes here, your tubes. So just let this sit and clamp one side. And then you calibrate it again. Yeah.
Just re-emphasize, you never, ever want to use the factory calibration. And many labs do it. This is why I'm emphasizing it. You do your own calibration. It's just like your spectrophotometer in the lab. You don't use the calibration that was done at BWR or Kerry when you use the spectrophotometer in the lab. Don't use it in this case as calibration.
This is probably your best calibration point to start with, right? After you put it into its frame and you calibrate it again, you should be able to match your own calibration. If you can't, it means you've tweaked your sensor. And so you just need to figure that out. Maybe you clamped it wrong or whatever. But make sure that you can get back to your original calibration. Then you deploy it, and you take it down to depth, you get the bubbles out. The upcasts usually aren't incredibly reliable because of the pump. And then you calibrate it when you go back. And you make sure that the calibration at the end equals the calibration on the frame, equals the calibration out of the box. Okay, so the highlight of today is calibrate. What are you going to be doing in the lab today? Yeah, it's fun.
In other words,
Yes.
this air valve, it's 50 cents a piece.
Right.
Without it, you're going to get crap data. So buy some extras.
Yeah,
It's a tiny valve.
it's a Y.
With a piece of white Teflon in it with a tiny hole, so that when air gets trapped in there, it bubbles up.
As opposed to being forced back into your sensor.
If you stay in your system and you have to be measuring bubbles, and bubbles are really strong scatterers, they can use your signal. So if you don't have it, cents piece that you allocate.
And you're spending 100,000 a day by the 50-cent piece. So often you'll see some profiles presented. This is from an AC meter where it's a function of depth, and you see, oh, it's beautiful. Look, I've got a mixed layer. I've got probably a thermocline or pycnocline here, and then the deep water's clear. Awesome, I'm ready to publish. And if you don't see the spectra of the data, be suspicious, right? A lot of people don't publish their spectra. So here is the spectrum from the mixed layer depth and from the deep layer. And yes, it's higher absorption here, lower absorption here. But look at the wavelength. What looks like that? Can you think of, is there any discernible component in those absorption spectra? Got a nice red peak, so maybe that's chlorophyll, but what's this? And why is it negative? Okay, so when you see these really nice spectra, this is exactly this data. Make sure that you look at your spectrum all the time. But when you apply your calibration, your water calibration, you realize that, oh, that detector was just out of calibration. And all it took was making one measurement with water, and you get these beautiful spectra, right? Okay. Calibrate, calibrate, calibrate. Here's an ACS. It's the same thing. So these are the pure absorption, pure water absorption and attenuation scans for pure water. Yes, they're negative because it's relative to the factory scan. And so you would have huge errors if you use the factory calibration relative to yours. And in fact, Mike Twardarski published a paper where he looked at one of the channels at 412, the deviation from the factory calibration as a function of time, and found that, you know, over a year, you have a pretty huge drift. And so you just need to make sure that you calibrate. You'd be off by 0.02 per meter. And depending upon your environment, that can be a really significant amount of signal.
And the drift happens also when it's on the shelf.
So that's not
Only
sample
by
data.
using- This is the jump between
This is
the
yeah.
first reports
Yeah.
and
This is on the shelf. This is when he was on a cruise. Yeah. Yeah. That's uncertainty, and you can take care of it. Okay, so here's the absorption by pure water. If you don't do the temperature correction for pure water, you have these really big dips, so you need to do that correction. If you don't, you'll have a big error in your absorption. So make sure to use the proper calibration standard, which is the water at the correct temperature and salinity. And this is uncertainty due to natural variability because you're profiling through water that has some temperature and salinity, and its absorption properties really are different. And so you want to make sure that you're subtracting a pure water of comparable temperature and salinity correction.
And it also means that when you calibrate, you write the temperature of the water when you calibrate.
Which you will do today. Okay, so again, I show you an AC9 because it's just not as pretty. It feels clunkier, and so you tend to notice errors, I think, more. Here's the beam attenuation as a function of wavelength. Here's the absorption as a function of wavelength, and what do you notice about the absorption? Looks like phytoplankton. I have a nice peak here and a peak here. There's probably some carotenoids that Ivona was telling you about. Is it ready to publish? Why? Because Skylar's got.
I don't know, the peaks just like don't line up with the wavelengths that you'd expect.
They may not line up where they expect. Maybe, and again, these are only, like this is 410, 440, and 555. So you might be missing a bunch of stuff in here because it's only 9 wavelengths.
I think also what she means is that the numbers are not in the right place.
Oh, and you're so right. I'm just going to cut and paste this over.
That would make more sense.
Yes, thank you for catching that. Yeah, this is a funny axis for that. Sorry. Yeah, so 676. Where's the whiteout? I can't even put anything over it. My shame. Let's put my shame over it and this won't even work. Oh. So, the first thing I notice is this. It's negative, right? So you do your temperature and salinity correction, and whew, It pops you right up. And it pops you right up here because, of course, a beam attenuation also has absorption in it, so it also has a temperature salinity correction. And so that's nice, but now we have this offset here. So we have to think about that. We're going to do the temperature and salinity correction here. So this is uncorrected, this is corrected. Once you correct for the variability in temperature and salinity, look how nicely those curves just collapse on top of each other. There were small variations here. So then the question is, what do you do about the scattering? What is this signal? That gets back to here. What is that signal here? We know that there is a scattering error in A. And if we've correctly done our temperature salinity correction and we still get an offset here, what's that signal? What do we do with it? Well, if it's phytoplankton, I already told you. It probably doesn't scatter. So that could be a scattering error. But what if it's non-algal particles in there? And that certainly looks like a non-algal particle absorption, or at least a CDOM absorption, right? So what are we going to do there? So that is an uncertainty. So here are some things to think about. The AC meters in the absorption side collects probably the first 40 degrees. Is it 40 degrees of the volume scattering function? Remember the volume scattering function from yesterday? It feels so long ago. 4 orders of magnitude. Most of the scattering is in the forward direction. That's all collected. It's the 40 to 180 degrees of the volume scattering function. From here all the way down here, that's back scattering, right? And side scattering. That's the part that isn't being collected. That's contributing to this uncertainty, this overestimation of absorption. So, here are some strategies. 15 years ago, Darius and Marcel said, subtract it. There's no signal out there. We're just going to take that value and subtract it, that value all the way across the board, just move everything down. Okay, it's the best we can do. So that says that there's no infrared absorption. It also says that the scattering is not a function of wavelength, because what we've done is subtracted spectrally flat scattering. Maybe. Okay. So this is what you might do in a spectrophotometer in transmission mode. And this is what we were doing with AC meters. There's another approach where you say, well, I know that scattering has a spectrum. And in fact, I can do a pretty good job of estimating it from my absorption measurement, my beam attenuation measurement, and if I subtract them, I get the spectrum of B to first order, right? And I can see that it's definitely not flat. So I'm going to assume that all of the signal here is scattering, and it's going to be some fraction of the total scattering. And I'm going to apply that fraction that I measured here proportionally along the spectrum. And so instead of removing a B that looks like this, I'm going to remove a B that looks like this. Okay. Which becomes really interesting when you talk about dissolved or almost dissolved period with really small particles, because they have a very strong spectral dependence of scattering. And so then I'm going to assume that there's no signal in the near infrared. And so we'll give you these equations. And what you would end up with is some spectral correction. Okay. So then Rudiger was making measurements with his integrating cavity absorption meter. And he said, you know, some of this signal is scattering. So you can't just assume that it's zero here. But it's not all of this. And so he did a bunch of experiments where he tried to come up with an empirical relationship to predict how much of the signal measured in the AC9 or the ACS in the red, how much of that signal is real absorption and how much of it is scattering. Okay. But it's an empirical relationship, so it's going to be different for you. And it's going to be different from you and different for you. So you have to, make your own, and if you go to a new environment, you have to do another one. And so what we're left with is that this is an active area of research. We don't know the answer, but we want to know the answer. So, project. Thinking about what is being measured here and how to correct for it is really huge, because it means that we can't do closure until we correct for this. Okay, so you'll see some of this today and tomorrow. Okay. What I can tell you, and I can be very specific about this, is that the answer is somewhere between 0 and what you measured. Thank you, Collin. And I could probably give you some pretty good idea about what the spectrum might be, but at least it gives you bounds. You can actually put an error bar on that and publish it and be totally honest and totally respected in the field, because nobody's doing better than that. Nobody at this point. Okay? Good. Okay. Yep, so you would compute your scattering if you've done your corrections. So, steps, calibrate, temperature and salinity correct both sides of your sample and your calibration water. Subtract your temperature and salinity corrected pure water calibration from your temperature salinity corrected sample. Do something with scattering. You should try a bunch of different ways to correct for scattering, see what the difference is between it, and then you'll compute your scattering spectrum. And those are the steps for the AC meters. So, I want to show you just one really cool example, something that Wayne Slade did when he was working with a manual. It's a way to get away from calibration. Dare I say it?
I mean, no, you use
No, it's good.
CDOM is the reference.
CDOM is your calibration. So if you measure your whole water sample, and then you filter it, and you measured your filter water sample, and you subtract them, what do you get? Particles. So your absorption by your particles plus your CDOM is your first measurement. Filter the water, you measure your CDOM, and you subtract them, you get the absorption by the particles. Well, in theory, you should have to have a pure water calibration here, subtracted to do this. You should have to have a pure water calibration here to correct that. If you're subtracting one from the other, you're essentially just subtracting it out, right? So you don't have to do it. So they set up a flow-through system where you could go, the water could come in and go directly to the AC9, or you could switch it and it would go through a filter and then through the AC9. Measured absorption as a function of time, which is also distance. Total sample, filter kicks on. Dissolve sample. Total sample, dissolved. And you just do that over time. And then you can interpolate between here, you can interpolate between here, you can subtract this from this. You get your particulate absorption, and look at this. Isn't this beautiful? This is absorption at 440. These are very clear waters. And when you look at the spectrum of the particles, you get this, 0.015. The red peak beautifully resolved at 003, 0025. That is almost the resolution of the instrument as reported by the factory, the resolution. But you're resolving a peak here. It's incredibly beautiful, incredibly powerful. So doing the total water sample and then the filtered water sample is your best friend, because you can have all of the errors in the world in your pure water cal, but when you do this, it all goes away and you can derive beautiful. So you're getting one of these spectra every point along here. And then you can begin to resolve features and slopes and non-algal particles, different pigments, phytoplankton functional types for Ivana. So it's incredibly powerful. Pigment-based taxonomy, yeah.
So there's a new twist to this method. Now people, what they do is they add a big drum of DI water that they produce every day, and they add another switch that goes to the DI because they want to see them data.
Yep.
So if you can do all three, and if the measurements are coherent enough in time, particularly for CDOM, that you don't go to big fronts or things like this, it might not be applicable to the particular spectrum you just measured. You want to make sure that everything is coherent, so you're looking at how much you change. Then you can do CDOM and...
And we actually have another switch, and we have two other filters. So we have 0.2 microns for CDOM. We have 2 microns, well, 5, and 20. So within our hour, we get total less than 20, less than 5, less than 0.2. So now you can get size fractionated absorption spectra underway, which allows you to begin to start thinking about ecosystem structure. Yeah. So, short answer, no. But you could imagine where you might think about something in here that oxidizes the pigment, which isn't great because the absorption shows up somewhere. Or the other thing that people do is you model it. So the great thing about non-algal particles, it's an exponential. So if you know something about maybe the absorption offset here, if you didn't scattering correct, it would give you some magnitude of that, and you could extrapolate it back with an exponential. There'd be a lot of uncertainty as you got to the blue, but it could be a first check if you know the slope. And then you could subtract that non-algal particle using modeling. I've done that before. It works. It's better than not doing it, but you just have to make sure you have your error bars.
What's the issue with passing it through an oxidizer?
Well, so what happens when you have pigments in here and you say add a little bit of bleach, the molecules don't go away. They just change their molecular configuration. And it turns out they really start to absorb more in the UV, and then you get a tail end of what was a pigment. And so your non-algal particle is pretty garbage. It's just, you have to be really careful in the blue. So it'd be better if there was some way to, I don't know. I'm sure someone in this room will come up with a solution in the next 5 years. Yeah.
Another thing is, in the process of this work, we discovered that you can use the deviation of the spectra from, and you see it with your calibration, from what you expect to tease out the temperature.
Oh.
The resolution of the ACS is such that you can actually use it to calculate the offsetting temperature, which is quite hard to do.
So you can either do it with beam C, which you know is going to have a relatively monotonic decrease, or what he's saying, if you have the dissolved absorption uncorrected, you know that this should look like this. So you can use that deviation in absorption to work out what your in situ temperature is, and then use that to correct your total absorption and attenuation. And more importantly, you have a temperature sensor. So you can profile and see the profile temperature just by using this deviation in your absorption spectra. So if you are ever at sea and your CTD dies, it's okay. You have an absorption meter. You have a temperature sensor as well.
And this, Andrew Garner, in earlier work, what he showed is you can use it to realize what's the delay in the water in your CTD and your AC meter. And so now you know, because you have a CTD on the rosette and you have your, or whatever platform you use, and you have this instrument, the delay in temperature between the two profile, these two is the difference in the position of the thermoblack will tell you how much you're delayed in time between the two instruments. So you can now align your features in the right place.
And also, if you have like a really strong thermocline with your CTD and with your absorption meter, if it's smoothed out, it's telling you that you have that the residence time of the water in your AC9 is spread out. So the features that you're seeing are also spread out. Yeah. So it allows you to back correct and get really sharp gradients.
Getting to that, we'll see exactly what it
Lunchtime. 1:30?
1:30 in the lab?
Yep.
Half of the 10 people here?
Yes, 10 people here and 10 people in the lab. You guys can self-organize.
And then you switch